So basically in structure of atom, what all terms we should know is first about discharge tube experiment. This is one thing we learned, discharge tube experiment. Through this experiment, we figured out what are cathode rays, correct? And when it comes to cathode ray, we learned the two important relations here. So this was as per J.J. Thomson's observation. J.J. Thomson's observation. So what we learned here was we can always equate electrical and magnetic field because cathode rays will divert or uh, bend across these magnetic and electrical fields. So we can equate these fields in the form of this. This is the formula for electrical field, and B into Q into V is the formula for magnetic field. From here we get to know that speed of particles will be always dependent on the ratio of electrical field versus magnetic field. And next part we learned is using this relation we got something called E by M ratio, which is also called as charge by mass ratio. Charge by mass ratio. And this ratio for electrons found to be a constant value irrespective of how E and B you change. Okay. And that is coming out to be coulombs per kg. So this is the first value you would remember, which is essential for JEE syllabus. Okay. What is the E by M ratio of cathode rays? Got it? Next. You would be typically asked what is the E by M ratio of particles, various subatomic particles. For example, if it is been asked for E by M ratio of proton versus E by M ratio of electron versus E by M electron of charge of neutron and E by M of alpha. If you want to take out the ratio for this. So one thing you need to understand here is that the charge of proton and charge of electron will be equal in magnitude, and mass of proton and mass of neutron will be equal in magnitude, and mass of electron is 1 by 1836 times that of mass of proton, and alpha particle is nothing but helium 2 and 4 2 plus, that means helium positively charged ion particle. So alpha rays are nothing but helium nucleus moving with a high speed. That's what we call it as alpha rays. Okay. So now if you substitute this back into this equation, and I also know that charge of neutron is 0. So it is neutral. Putting all of these into uh, options here. So we'll get E by M ratio of the particles will be E, which is same, and mass of proton I'll write it as 1836 times of mass of electron. That is to, okay, E by M of electron. Okay, this is for electron I'm writing, and 0 by M, which is the ratio for neutron, and charge of helium would be 2 times the charge of proton divided by mass will be 4 times the mass of proton, and mass of proton is 1836 times of that of electron. Okay, so I can remove this M here and replace that with this number. Okay, now if you notice the ratio which we can take, correct, this will be anyway 0, and E by M, E by M, E by M will get cancelled here. Okay, so what do we get here? The ratio will be 1 by 1836 is to 1 is to 0 is to, this would be 1 by 2 times of 1836. So in case if I multiply this by 2 times of 1836, I will get this as 2 divided by 1836 each to 0 is to 1. Okay, so this is a very important value that will be asked in JEE. That is, what is the ratio of proton, electron, neutron, and alpha particle. Okay, please check this out. If you have a problem, you can ask me now. Everybody comfortable with this?
Yes, sir.
Right. Okay. Next, we learned something called Millikan's oil drop experiment. Millikan's oil drop experiment, which suggests that we can absolutely figure out what is the mass of electron and proton. The mass of electron as found out to be 9.1 into 10 raised to the power of minus 31 kgs. Mass of proton was found out to be 1.67 into 10 raised to the power of minus 27 kgs, while charge of electron will be same as, you know, 1.602 into 10 raised to minus 19, and charge of proton will be same value except it will be in a positive sign. That's it. This is what you will get to know. Okay. Again, we will not have to go much details about Millikan's oil drop experiment. That will not be asked much in JEE. Okay. Next, we learned about elemental representation. The next part we learned about elemental representation. That is how to represent the elements. Typically, any element will have two main parameters. One is A and one is Z. Okay. A represents mass number, which is basically number of protons plus number of neutrons present in the nucleus. And Z is the atomic number, which is simply number of protons. Correct? Just a second. Sorry, check. So this is number of protons. Okay. So for any element, you will always have these two parameters defined. So based on these parameters, we can always relate any two elements. For example, there are different terms that we need to use to relate the elements. One of them is isotopes. Isotopes means having same Z value but different A value. Okay. For example, hydrogen 3 1, hydrogen 2 1, hydrogen 1 1. This is called tritium. All of them are hydrogen family, and this is deuterium, and this is protium. Okay, all of them belongs to hydrogen, but they are three different uh, elements, correct, of a same family. Next term we need to understand is isobars. Isobars as in same A value but different Z value. Got it? That includes like potassium. If you have 4019, it is one of the isotopes of potassium. Calcium, which is 4020. Argon also has 4018. So all these three are isotopes of each other. Sorry, isobars of each other. Another definition we have is isotones. Isotones is about same number of neutrons. Should have same number of neutrons. That is same A minus Z value. Correct? For example, if you take chlorine 37 and 17, the difference is 20. Calcium 40, 20. Difference is 20. Argon 38 and 18. Potassium 39, 19. All these four are isotones of each other. And lastly, isoelectronic species. Isoelectronic species. Isoelectronic species means simply same number of electrons present, total number of electrons present. For example, C4 minus, N3 minus, O2 minus, F minus, Ne, sodium plus, Mg2 plus, aluminium plus 3. Now, number of protons are different here. So this is 6, 7, 8, 9, 10, 11, 12, 13. Protons means mass number. Z value is different. But what about the number of electrons here? Number of electrons are exactly same. This 4 minus represent in a neutral carbon we have 6 electrons, but now adding another 4 that makes it 10 electrons. So all of them in fact has 10 electrons in total. So these are isoelectronic species. Got it? This is a basic introduction that you need to know it from structure of atom. The next thing we learned, okay, a little bit in more detail is about Rutherford's gold foil experiment. Gold foil experiment. Here, mainly we learned about how the alpha ray particles, for example, if alpha ray particles are traveling this way and they are bombarding the metal surface here, let's say this is a gold surface here like this. This is a gold surface here, a gold foil. So it has been observed that most of the alpha rays penetrated through it, but very few got deflected like this. Okay, in fact, some of them even bounced back like this. Okay, and one of the alpha ray even bounced straight back to this. This is a kind of observation we saw from Rutherford's gold foil experiment. Got it? So what has been found here is most of the space is empty. Okay, most of the space in an atom is empty, and the deflection is because of positively charged, right, nucleus, which has most mass of the atom, most mass of the atom. So most of the mass of the atom is present in that positive charge. Okay, right. Next, we learned that rarely any alpha particle will deviate back. Okay, that means it will go or it will bounce back. Just a second. Right. Okay. So check this out. So positively charged nucleus, which has most of the mass present in it. And one of the important conclusion is 1 out of 20,000 alpha rays, okay, bounce back. That will bounce back. Clear? Right. Study 1 out of 20,000 alpha rays will bounce back. And what are all the other important conclusion? What he understood is that approximately radius of an atom, whether it is gold or any other element, where the scattering is observed, will be in the range of minus 10, 10 point minus 10 meters. And approximately radius of the nucleus will be in the range of 10 raised to power of minus 15 meters. Morning, please. Morning. Okay. Volume of an atom by volume of a nucleus, if you compare, it is 4 by 3 pi r cube of atom by 4 by 3 pi r cube of nucleus. So if you do that, it is coming out to be 10 raised to power of 15. So which implies that the volume of an atom is around 10 raised to power of 15 times bigger than that of volume of the nucleus. Now, this has been a very, very frequent question in JEE that you should remember how volume of atom and nucleus are related to each other. Okay. Another important relation which you would be learning more in physics, but I mean, which will be using application more in physics, but it's an important formula, anyways. That is radius of nucleus, correct? Rn will be equal to R naught into a raised to power of 1 by 3, and R naught value is approximately 1.3 into 10 raised to power of minus 15 meters into a raised to power of 1 by 3, and a is mass number. So that means if you simply know the mass number of an element, you can approximately predict what could be the radius of the nucleus. Okay, it was a very important breakthrough, everybody. So these were the important pointers that we learned from Rutherford's model. Okay, one another part which is been asked is scattering angle. How much is the scattering angle of alpha particles? That means how many number of particles are making 10 degrees scattering or 20 degrees scattering or any theta degree scattering. So that would be n theta is proportional to 1 by sine raised to power of 4 theta by 2. So simply remember it like a formula. Got it? So if you want to compare how many 10-degree rays versus how many 40 degrees rays, or how many 30 degrees rays versus how many 45 degrees rays, so you can simply use this formula, compare the ratio. Okay, so which means if you are comparing any two degrees, so you will compare it like this: n1 theta by n2 theta will be equal to sine 4 raised to power of theta 2 by 2 divided by sine raised to power of 4 theta 1 by 2. Okay, right. This is about Rutherford's model. Next, Rutherford's model has one very important challenge to observe, that according to him, electron revolves across the nucleus in circular orbits. It will across the nucleus in circular orbits. Okay. Now, when it comes to circular orbit, this is how typically what I meant. This is nucleus. Electrons are moving in various, having this particular direction at every different point. It is moving in circular motion. Got it? But this is where the next important theory comes into picture. Correct? Uh, which is about Maxwell's electromagnetic theory. Got it? Now, let's understand something more detail about it. According to Maxwell's EM theory, according to Maxwell's electromagnetic theory, he suggests that any charged particle, any charged particle in magnetic or electric field, if under acceleration, will lose energy, in the form of waves, and he called that waves as electromagnetic wave. Got it? This is the basic premise of Maxwell's electromagnetic theory. Got it? That means if electron is moving across the nucleus like this, that means it is under acceleration. Since it is under acceleration, it is bound to lose the energy. If it loses the energy, electron eventually will spiral and fall into the nucleus. But but the atom is pretty safe and it is stable, which means electrons are not actually losing out their energy. So that means some problem is occurring in the formation, in the way Rutherford has explained that theory. Correct? So to get into more details about it, we need to understand two important aspects of waves, okay, or two important aspects of charged particles. See, charged particles can behave more like waves or also like particles. Got it? And particle behavior is something which is easy to understand. So first, what we will do, we'll try to understand what is the wave behavior. To know that, we need to know something called wave characteristics. And that's what we learned. I'll just quickly brush it up once, check it out. One is wavelength. Okay. Wavelength basically is the distance between, suppose if this is the wave, it is going like this. Then how much is the distance between, two crest or two troughs, which means distance between this to this. This is distance between the two crest or distance between the two troughs. Next, we discussed about frequency. Frequency represented as the letter nu, okay, like a v but like this, nu. Okay, we call it as nu. Nu is the number of waves per unit second, per unit time. Got it? And the units for it will be second inverse, so which means nu is simply 1 by time. Then we have amplitude. Amplitude is about height of the crest or depth of the trough, like this. If you have a wave, this height is what we call it as amplitude. Okay. And intensity of any wave, intensity of any wave is directly proportional to amplitude square. Just for now, remember it. You will be learning more in details in physics about how it is related. But for us, just need to know the term. That's all. Okay. Next, how do we define the speed of wave? Speed of wave. So speed can be represented as some velocity v, that is equal to how much amount of wavelength it is been traveling per unit time. So lambda into 1 by t, if you write it, it can be written as lambda into nu. And for electromagnetic wave, it is been observed that the speed is a constant value, and that value we represented as speed c, which is 3 into 10 raised to power of 8 meters per second. So c will be nu lambda, and this value is always constant value in vacuum. Correct? These are important wave parameters, because there is one more term of wave parameters which is called as wave number. Wave number, which is represented as nu bar, which is nothing but number of waves per unit length. Number of waves present in unit length. How many waves are present in unit length? So that represents wave number. Got it? So these are few important wave characteristics we should know. Got it? Now, when it comes to electromagnetic radiation, unlike any other radiation, here, when it comes to electromagnetic radiation, it will have two different components present in it. The first component will be like this, where it is going almost parallel to one of the axis and propagating in the other axis like this. Okay. And the other form would be like this. It will be going in this direction like this, and both of them will be perpendicular of equal wavelength. You can see they have equal wavelength, but they are perpendicular to each other. Okay. So we can say that if one component is electrical component like this, the other one will be magnetic component, and they will be perpendicular to each other always. Correct? And they propagate always uh, in a perpendicular plane. Like for example, if this is the direction of electrical field, it will propagate in this direction. If this is the direction of the magnetic field, that also propagate in this direction. Okay. So for electromagnetic radiation, we will say that C is equal to nu lambda. Correct? And light, sunlight or any white light, sunlight or white light is is an is an electromagnetic radiation, EMR. Remember what is EMR? Electromagnetic radiation, a wave which has both electrical and magnetic components present in it. Okay. Now, usually when it comes to white light, let's say it is sourcing from sun. Okay. Usually, sun will always send the electromagnetic radiations in a bunch of radiations together. Got it? And when radiations come together, radiations propagating together, propagating together, we call it as electromagnetic spectrum. We call it as electromagnetic spectrum. Okay. So when it comes to spectrum, if you open up the entire spectrum for coming from sun, you can actually categorize them into various sections here. Okay. So like this, you can categorize them into various sections. Okay. The first section, which has high frequency, are gamma rays. Okay. The next section is UV rays. Next section is visible rays. Got it? Sorry. Next section is X rays here. After gamma, it is X rays. Then we have UV rays. Then visible rays. Correct? Then infrared rays. IR means infrared rays. Then microwaves or micro radiations and radio radiations or radio waves. Got it? Usually the cell phones, right, which we use, they always operate in various radio waves. Okay. So one thing you can understand that this is a direction. Okay. This is a direction in which wavelength lambda increases and frequency decreases. Got it? Typically, this is the range. Okay. Now within the visible region, invisible region, it starts from Vib Gior, right? And from here to here again, if you notice from here to here, what's happening to the wavelength? Wavelength is increasing, frequency is decreasing. So highest frequency is for violet color. Got it? So this is the fundamentals of wave behavior. I hope all of you got this. Please check once quickly. All good? Everybody?
Yes, sir.
Right. Now listen up. The next part, what we learned was about how do we derive the wave characteristics. Okay. So wave behavior can be explained mainly by two phenomena. First one is interference. The other one is diffraction. These two phenomena explain the wave behavior of light. But I'm not going into details of that because we have a separate topics altogether in physics. So you'll be spending a lot of time understanding the topic itself. What is interference? What is diffraction through it? Okay. But for our intention mainly in chemistry is to emphasize on the particle behavior. Okay, so let me take that. So let us see that particle, yes, okay, particle behavior. So please check it. What about the particle behavior? See, there are three phenomena which explains the particle behavior. One is black body radiation, black body radiation. Okay. Second one is photoelectric effect. The third one is hydrogen spectrum. These three phenomena explain the particle behavior. Got it? Out of which the first one, if you see BBR, black body radiation, correct? Main emphasis on the black body radiation is about, we use a material called black body. So black body is a perfect absorber of light and perfect emitter of light. Okay, so that means it will absorb all the radiation. It will absorb all the radiation and also it will emit all the radiation when it is in need. Okay, got it? For instance, if you notice, suppose if this is a black body and there is a small hole which is being made in the black body. As the light enters into it, see what we see any wave. If you are watching a light, we always see it in the form of wave. Okay. So another simple observation which you can remember to assess the wave and particle behavior is like this. Okay. Correct. Microscopic particles. Microscopic particles observe the light as microscopic particles observe the light as particles, while macroscopic particles or macroscopic particles like us, material like us, we observe it as, okay, that will be wave behavior. Got it? So for us, you can see wave only. For us, light is observed as a wave. But for very microscopic particles like electrons, they will assess the light as particles. Correct? So just keep that in mind for now. So for us, we are watching like waves entering into the blackboard, and each has different wavelength, lambda 1 and lambda 2. After entering, they might start interacting inside, right? They have to, as per our knowledge, what is happening inside is these waves might interact with each other like this. Everywhere it will interact. And uh, if you start heating this black body, you expect those radiations to come out again. So we are expecting now the same radiations will come out of it. Got it? But what is astonishing to observe is that if it comes to lambda 1 and lambda 2 here, after mixing with these two, there should be a phenomena of interference. That means there should be a new lambda which could be greater than or less than lambda 1 plus lambda 2. But unfortunately, what has been observed, the new lambda is not been observed. Rather, you'll only see lambda 1 and lambda 2 perfectly coming out the way they went inside. The way they went inside, they are coming out perfectly the same. Which means if there was any kind of interaction like this, which is called interference, then the overall wavelength should change and new waves must have come. But that is not happening. We are rather seeing the same waves coming out. This suggests that interaction with the inner core of the black body is not happening like a wave, but it is happening like a particle. Got it? And as per black body radiation, Planck has observed some very important experimental observation here. That is, when you try to plot intensity versus various radiations at different temperatures, like temperature T1, T2, T3, then you will start observing two important things. One, a black body literally use almost all the radiations. This is I versus lambda. That is, you can see this is all the range of wavelengths. But at a particular temperature, one wavelength will be always maximum intense. So let me call this as lambda 3, lambda 2, lambda 1. Now, as the temperature increases, that is T3 greater than T2 greater than T1, then what is happening as the temperature increases? Lambda max value decreases. That means as you start increasing the energy, that means you are increasing the temperature. Then the maximum value of the wavelength, right, is decreasing further. Okay, lambda max of a particular intensity is decreasing further. Got it? So here there are two things which we can observe. One thing is Wien's displacement law. Wien's displacement law. According to this law, for a particular lambda max at a particular temperature, the product always remain constant value. This will always remain constant value, which means lambda 3 T3 will be same as lambda 2 T2 will be same as lambda 1 T1. Okay. So you better remember this. In fact, you will be learning all of this again in modern physics in 12th standard physics. Okay. Got it? Second thing, what Planck has observed, Planck's observation is that he assumed that energy, since it is increasing, the lambda value of a particular kind is decreasing. So he related these two terms and said that we can write this as hc by lambda, or simply h nu. Sorry, this is equal to h nu. So he called the energy which is absorbed in the form of small packets. In simple terms, imagine for us we are viewing a wave like this. Just for the sake of understanding, imagine the wave is going like this. Like this. Okay. This is what we are observing when we are sending the wave, or when we are observing as it comes out of the uh, black body. But how the black bodies are observing this one? They are observing like there is one energy packet here, then there is next energy packet here, next energy packet here, and next energy packet here. So they are interacting, the inner core of the black body is interacting the light as this, you know, packet of energies. And he said that this packet of energy can now be related to hc by lambda. The lambda is the one which we are observing like this. Clear, everybody? Or we can write this as h nu. So this is called as quantum theory or energy quantization theory. Quantization of energy. Okay, that is representation of energy in the form of small energy packets. Everybody clear? Now, if you leave it for a longer time, there will be a lot of quantum particles which are falling in. And what is Max Planck decided to call it? He called every packet of energy as quantum. Okay, if source is light, if source is light, that means white light or sunlight or starlight, then we call the quantum as photon. We call it as photon. So that means energy of one photon is h nu. Okay. And he also said that energy of n number of photons. That means if you have n number of photons present, then energy can be represented as nh nu or nhc by lambda. This will be the energy of photon, everybody. Got it? Sometimes in the questions, instead of directly giving the energy, they will give you another term called power. Okay, power of, you know, power of light. How much is the power of light, or how much is the power of quantum which we are observing? So power by definition is energy upon time. So from here you can write energy is equal to power into T. So the same equation can be represented as power into T is equal to NHC by lambda. Now this becomes a very important formula for solving questions. Clear everybody? Please check what is quantum theory and what is black body radiation, everybody. If there is a doubt, you can ask me now.
So could you just explain the graph again, and could you also explain the E equals to HV?
Sure. Please check. See, since I'm using the definition perfect absorber and perfect emitter, which means we expect the black body to absorb all the radiation that is falling on it. And in contrast, when you start heating it, it is supposed to release all the radiations also. Now, this plot is about plotting all the radiations at a particular temperature. In simple terms, compare if you have an iron rod and you are heating it over time. Iron rod is not non-perfect black body. It is not perfect black body, but it's a non-perfect black body. It's not an ideal black body. Even then, if you start heating the iron rod, you would definitely see some radiations are coming out of it. In fact, you can feel the heat of the iron rod, which means it is dissipating infrared rays. The heat which we feel, even when you go in the afternoons, the heat which you feel is because of the infrared rays coming from sun. Okay. Second thing, you'll also see the color of that iron rod, isn't it? It
Yeah.
would rather start going from orangish to yellow to green to blue and so on. Different colors, it will keep going. Basically, iron rod is actually releasing all the colors, but one color distinctly is observed very bright for you, isn't it? Highly intense for you. That is that lambda max which is plotting. Understood? So probably if I compare this as an iron rod graphs, so I can say this is at a temperature T1 when we are noticing this as a probably red color. Then we are observing it like a green color. Then it is observed as a blue color. Okay, beta. So this graph represents what is the intensity of all the radiations across the spectrum at a particular temperatures. Clear? Kapil, I hope you
Yeah.
understood this part.
Yeah.
Right. Okay. Coming to the second part, that how he related this phenomena with particle behavior. Simple. If all of these radiations, the way we have sent, it is coming out the same way it is coming back, which means you are not able to see something new. It is the same waves which are going in, same waves coming out. Now, if the waves are going somewhere in a confined space, they are bound to interact with each other and change their wavelengths. That is the phenomena of interference, beta.
Yeah.
But there is no such phenomena happening here. The way they are entering is the same way they're coming out. Is that clear? Which means precisely it is interacting with the inner core of the black body as a particle. So the light is going according to the inner particles of black body. The light is coming like a packet of energy. So it is accepting that energy, keeping it stored. When you are heating it, throwing it out. That's it. So for us, we will not be able to see any difference in the wave.
Hmm.
Clear? That is also used, the black body is used as an application using Wein's displacement law. And Planck's also has been able to derive a very important equation, that is energy of a photon, which is equal to h nu or hc by lambda. All good?
Yep.
Right. The next phenomena which we learned was about photoelectric effect. Photoelectric effect. Okay. So according to photoelectric effect, if you have any metal surface on which you are sending a monochromatic light, okay, then it is expected that the surface electrons present on it will eject. They will probably eject. And these electrons move all the way towards an electrode connected in a confined space. And if these electrons reaches here, we can actually store them in a capacitor like this. This way it is connected. Got it? Okay. So this phenomena where we are able to generate a voltage difference between the two electrodes using using the electron flow coming from the surface of a metal surface, that is called as the photoelectric effect. Okay. So in simple terms, ejection of electrons, ejection of electrons from surface of a metal. Got it? So in short, suppose if there is an electron here, a packet of energy is falling as h nu here. So this electron is taking that energy, coming out and gaining some kinetic energy. Okay. But what is happening here is this energy which is going as a packet of energy, correct? First, it will make sure that it will separate the electron from the surface. To do that, because electron is bounded on the surface, that means it has to overcome something called as a binding energy. It has to overcome that binding energy. So it will bargain with the surface. It will give some energy to the surface to pluck itself out, and rest of the energy it will convert into kinetic energy. So this is typically what is expected out of photoelectric effect. So energy of the source, right? Or we call it as incident energy, incident light will be equal to binding energy. Binding energy is called as the work function. Binding energy is called as the work function W naught plus kinetic energy of the electron. So in short, we write this formula as E is equal to W naught plus kinetic energy. So this is the formula for photoelectric effect. E is energy of one photon. One photon is h nu. That is equal to W naught. W naught now can be represented as h nu naught plus kinetic energy. That means I am representing the binding energy in the form of photon energy required. This much is the photon energy that is required. Okay. So that plus kinetic energy. Here, nu naught is known as the threshold frequency. Threshold frequency. That means frequency, which means it is minimum frequency for electrons to eject or perform photoelectric effect. Correct? And Ke is the maximum kinetic energy because there is no other loss of energy. So this is the maximum kinetic energy of electron ejected. Okay. So this would be using a lot of times. So h nu can be represented as hc by lambda. That is equal to hc by lambda naught plus kinetic energy. Okay. Now listen up some unit conversions. Unit conversions. Got it? See, first of all, h is a Planck's constant. Its value is 6.635 into 10 raised to power of minus 34 joule second. Now, if I write in terms of energy as hc by lambda, c is also constant value, which is c is 3 into 10 raised to power of 8 meters per second. So we can write the energy as, 2 into 10 raised to power of minus 25 by lambda in meters, right? And this will be joules per atom or joules per electron, whatever, or joules per photon. This much amount of energy is present in one photon. Now, in short, I can also write this as this is per photon of energy, right? What if there is 1 mole of photon? Now, you need to understand one more representation. 1 electron volt is the energy carried by one electron in carried by an electron in a 1 voltage difference field, and that value is 1.602 into 10 raised to power of minus 19 joules. Okay, which is same as the charge of electron, if you remember, right? So this amount of joules, if at all I convert that into electron volts, That means I have to divide this number here. So as I divide it, I will get this as 12,422. Okay, 422 divided by lambda, or simply 420. You can take it as 12,420 lambda in Armstrong units. This will be electron volts per photon. So a lot of time this formula is what we'll be using. Okay, and notice the representation of this new units. 1 Armstrong means 10 raised to power of minus 9, sorry, minus 10 meters. 1 nanometer means 10 raised to power of minus 9 meters. And if I write in centimeters, it is minus 8 centimeters, and this is minus 7 centimeters. And 1 picometer is 10 raised to power of minus 12 meters, or 10 raised to power of minus 10 centimeters. All good. So this is how we can relate the Armstrong nanometer and picometer. Everybody clear on these terms? Right. So these are the units which we'll be using for solving questions here. Okay. And now notice this one. When it comes to intensity of radiation, okay, in photoelectric effect. So you will see lambda or nu is a constant value. It is a constant value. This is constant only. Okay. But number of photons are changing, which means if at all I'm saying 5 photons per second versus 10 photons per second, if I say the intensity here is I naught, I would say the intensity here will be 2 times of I naught. So in short, intensity is directly proportional to number of photons ejected. More the photons ejected, more is the intensity. Simple. So intensity depends upon only one term, that is how much is the number of photons moving. Okay. So graphically, you would notice something, that if you plot between intensity versus number of photons, right, you will see the graph going this way. That means it will go linearly. Correct. While if you compare the same thing with kinetic energy, so no matter how much amount of kinetic energy changes here, got it? How the kinetic energy, how the intensity changes here, the kinetic energy remains constant. Got it? This is the way you need to check. And if you compare this with photocurrent, okay, something called photocurrent. What does that mean? Suppose if you are plotting current that is developed due to the ejected photons versus intensity. So if intensity is increased, current will also increase. Got it? So this is something we need to understand from photoelectric effect. And the last graph, shall write it here. This one you can see where we are plotting kinetic energy. Okay, kinetic energy versus frequency. So for a particular ejection of photons, ejection of electrons, this is the way it will vary. Correct? Where this is exactly stopping at nu naught. So when, if you give the energy of a photon equivalent to mu naught, electron will just eject, but it will not gain any kinetic energy. Okay. So how is the equation here? You know that kinetic energy is equal to h nu minus h nu naught. So if this is angle theta, I can say tan theta is equal to h, and y-intercept, which is c, is equal to h nu naught. Okay, so this is like y is equal to mx plus c. So you can see the intercept is negative, so that's why it is a negative intercept value. This is c. I hope all of you got that. What is photoelectric effect? Any doubt here? Please do ask. Tanmay, are you able to get it, beta?
Yes, boss.
Sir, can you explain the second graph once again?
Sure. See, basically, intensity is only about how many number of photons that you are adding, but it is not changing your lambda and frequency. And you know, the kinetic energy only depends upon h nu, which is equal to h nu naught plus kinetic energy. If this remains constant, this is anyway constant value, so kinetic energy has to remain constant. Okay, so even though the intensity is more, which means more number of photons are falling per second, the number of electrons ejected may be more, but the energy that is carried, the kinetic energy that is carried by every electron will remain same. Clear? That's why
Yes, sir.
as the intensity increases or decreases, kinetic energy remains the same. Clear, everybody?
Yes, sir.
Right. Now, the next important part that we need to discuss is about Bohr's atomic model. So check out Bohr's atomic model. Bohr's atomic model is applicable for stationary orbits or shells. Stationary shells means he believes that electrons revolve across the nucleus in circular path. That circular path is what we call it as stationary orbits. Got it? And each orbit, right? Suppose if you have one, we have two, and third one, like this. If you keep on going across third one, fourth one, fifth one, like this. Okay, so this is nucleus. So each orbital he designated with an alphabet starting with K. So this is called K shell, L shell, M shell, N shell, and so on. And each orbit is also designated with a number. N is equal to 1, 2, 3, 4, and so on. And he believes that electron will always rotate in a particular orbit only. It will not be found anywhere in the space existing between the two orbits. It will be either this or that. So which means the position of electron is also quantized. The position of electron is quantized. Okay, it will be always fixed. Quantized means fixed value. Fixed value. Got it? And as long as the electron is present in the nucleus, it will always keep its energy constant. So to keep the energy constant in a circular motion, what a particle must do? Okay, a particle must conserve angular momentum to keep energy constant. And according to Bohr's model, mvr, which is angular momentum, is been a constant value of h by 2 pi, and n is an integer value, simple integer value starting from 1, 2, 3, and so on. Okay, where mvr is nothing but the angular momentum. Okay, how much is the momentum it is carrying when it is moving in a circular motion. Got it? Again, we don't have to get into the proof of this, how he got it. We just need to remember the formula that mvr is always a constant value, and the constant value is h by 2 pi, and n is an integral value which is multiplied as per the orbit number. If electron is present in the fourth orbit, it will be 4h by 2 pi. If it is present in the first orbit, it is simply h by 2 pi, and so on. That's how it is quantized. Okay. Now, he learned something very important. Mathematically, he was able to prove what is the energy of an electron, radius of an electron, and speed of an electron. These three I was able to calculate, correct? To do that, we learned that we can use the derivation here when electron is present, you know, somewhere away from the nucleus at a distance r, and it has this angular linear momentum as mv. Okay, then there are two forces which you notice, that one force is trying to pull inside, which is called as centripetal force, and one force is trying to pull it outward, which is called as centrifugal force. So this is centrifugal force and this one is centripetal force. Now centripetal force is because of the charges, and any two particles, charged particles, oppositely charged particles, if they are attracting, we call it as Coulomb force, and the Coulomb force will be equal to some constant into m1 some constant into q1 q2 by r square. This is the formula. And centrifugal force, which is outward force, is equal to mv square by r. Okay, again directly use this as a formula, do not worry about derivation. Okay, now equating these two, what is the charge of a nucleus? Charge of a nucleus is Z, which is the number of protons, into energy charge of one proton, and Q2, which is the electron charge, is E. Hence, I can write Coulombic force or centripetal force as K Z E square by R square, and centrifugal force as M V square by R. And at, you know, if electron is present in an orbit, then centripetal force has to be equal to centrifugal force. So therefore, kz e square by r square must be equal to mv square by r. And now another important point is, we know that mvr is equal to nh by 2 pi. Okay, and if I square this on both sides, I will get this as m square v square r square is equal to n square h square by 4 pi square. From here I can write it as mv square is equal to n square h square by 4 pi square into m into r. Now substituting this back into this position here, if at all I use that here in this equation, I will be able to derive the value of r. Got it? I know how much is the value of r you are getting. This is the formula you will get. That is, radius of the nth orbit of a Bohr's model will be equal to n square h square by 4 pi square m into kz e square. This is the value what you get. And you notice that these are all constant values. H 4 pi square, mass of the electron, k value, z value, sorry, not z value, e value, these are all constant values. Putting all the constant values, you will get this value as 0.529 into 10 raised to power of minus 10 into n square by z in meters. Okay, so this is the nth orbit, and this value you can also write it as r naught. So r naught, or simply a naught, n square by z. Okay, this is the formula that will be used to figure out the radius of the nth Bohr's orbit. Okay, radius of the nth Bohr orbit. Clear? So from here, the picture is very clear that if at all I am finding out the radius of the nth orbit for hydrogen, and I compare that as the radius of the nth orbit of helium plus, right? So definitely radius of hydrogen is greater. And if you check out the second orbit of the hydrogen, that is definitely greater than the first orbit of hydrogen. Okay, this is the important conclusion you can draw. Everyone clear about the radius? Please check quickly. Everybody, all okay? Right. Now, notice the speed of the second part we need to learn is about speed of electron. Speed of electron. You know that mvr is equal to nh by 2 pi, and just now we have learned about how to represent the r also. R naught can be written as r naught n square by z into mass m. So that will make it some constant v naught into z by n value. And this constant value V naught is found to be 2.16 into 10 raised to power of 6 meters per second. So you can see speed of third orbit of helium plus is greater than speed of third orbit of hydrogen, and speed of third orbit of hydrogen is less than speed of second orbit of hydrogen, correct? Because it is directly related to z but inversely related to orbit number. Okay. Right. So the next important factor we have to learn is about the energy of electron. Okay. Let's check. We have, if this is a nucleus here, okay, and it is at a distance r here, correct? If electron is moving, then it will have two parts here. Total energy of the electron must be how much is the kinetic energy of the electron at that point of time, and how much is the potential energy of electron at that point of time. Okay, so potential energy is equal to force into distance, got it, which is equal to centripetal force into r with a minus sign. Why minus sign? Because you see, force of attraction is inward but electron is trying to go outward, so these two vectors are opposite to each other. So, and it is a uh, what do you say, there is a cross product here, so therefore these two multiplications will always be minus. So that is equal to minus kz e square by r square. We just learned this as the centripetal force into r, which is equal to minus kz e square by r. This is potential energy. Kinetic energy is equal to simply half m v square, which is equal to half into mv square. We learned it as kz e square by r already. So you can see the total energy sum of these two. So after adding these two, you will get this as minus half of kz e square by r. So this is the total energy what you will get. Clear? So this is the total energy of electron. So in short, you can see the total energy value is half of that of potential energy, correct? And total energy's magnitude is same as kinetic energy's magnitude. Got it? So this is an important part we need to learn. Now, how do we get this energy now? So total energy is this value. So I need to just replace this R with that formula. So therefore, total energy is equal to minus 2 pi square k square into m e raised to power of 4 divided by h square into z square by n square is what you will get after substituting that R value. And you know that these are all the constant values. So I will get this as minus E naught Z square by N square. And this E naught value varies right from 13.6 electron volt per atom, okay, or it is 21.7 into 10 raised to power of minus 19 joules per atom, okay, or if you write it in moles, it is 1312 kilojoules per mole, right, per mole of atom. This much is the total amount of energy of electron which is carrying. Clear? Now you can clearly notice that total energy as it increases, total energy increases, which means n value is increasing. You can see as the n value increases, the negative value becomes more towards zero, which means overall it is an increment. Negative, if it is coming towards positive value, that means there is an increase in the energy. Okay. And while total energy value decreases or it becomes more negative as the Z value increases. So which means if you talk about various atoms, right? The atom which has a higher Z value will have a lower total energy value. Got it? And here there is one important term we need to know, what is known as ionization energy. Ionization energy. Correct? IE. So ionization energy basically suggests that it is E naught into Z square. So E naught value is 13.6 into Z square. That is, this is the amount of energy which is bounded with the particular orbit. So if you remove this energy, right, if you add this amount of energy or supply this energy, electron will be completely escaping out. Okay. So which means if total energy of an electron in the first orbit is minus x joules, then ionization energy will simply be equal to plus x joules. Okay, if total energy is minus, ionization energy will simply be plus of that value. That's it. Okay, but ionization is precisely defined more for the first orbit. So you can see this is the energy required for first orbit. Okay. Now the energy difference is something which is very important for us. Okay, so for hydrogen atom, if you compare the nth orbit energy, if you compare one by one, right? So that is if n is equal to 1, it is 13.6 electron volts. If n is equal to 2, it is 3.4 electron volts with minus sign. Okay. N is equal to 3, it is minus 1.51 electron volts. Okay. And n is equal to infinity, it is 0. Now notice the difference in the energy also between these two. How much is the difference? Between these two, how much is the difference? And between these two, how much is the difference? So that difference is directly asked in solving questions. So please do remember the difference between these two is 10.2 electron volts approximately. And the distance between these two is 1.89 electron volts. And difference between these two is 12.1 electron volts approximately. Okay. So especially you will be asked for first order, second order, and third order. Got it? I mean first orbit, second orbit, and third orbit. How much it will be the value? Okay. The next important aspect of uh, Bohr's model, you will notice that as you move away from the orbit, the energy value is increasing. Correct? So which means the energy difference between two orbits, energy difference between two orbits, okay, decreases as moving away from nucleus. Moving away from nucleus. So you can notice that here delta E, that is energy difference between two orbits is N2 minus N1. This is how it is. Delta is equal to N2 minus N1. Now the important factor what we have to understand is that if let's say electron is going from first orbit or any nth orbit, this let's say is N1 orbit to N2 orbit. If electron is jumping from N1 orbit to N2 orbit, that means it is absorbing some energy. Okay. So to absorb some energy, it has to absorb the energy only in the form of photon. It will absorb the energy in the form of photon. And this energy should be same energy difference of N2 minus N1. Energy of N2 orbital minus N1 orbital. And the same logic works the other way around also, which means when electron is coming back, let's say if electron is present here and it is coming back here, okay, then it will release the energy of the same energy packet. Correct? So how much amount of energy it absorbs is the same amount of energy it will throws away. Got it?
Where is the energy coming from?
Where is the energy coming from? Energy is being supplied in the form of light. Got it?
Yes.
Okay. In fact, for example, if you notice the uh, almost if you notice the color of my t-shirt, it's little turquoise. Okay, almost like green and bluish, right? Now, how are you able to see that color, by the way? There is a white light which is falling on it. The surface electrons are going to some higher orbit by absorbing some energy. Okay, and out of the white light, it has absorbed some energy, and rest of them is reflected out. The reflected light is what you are able to see. Got it? So that means whenever there is a light on, there is a continuous absorption of energy of the surface electrons and they are going to the higher orbits. Okay. And would they stay there for a longer time? No, they'll continuously come back also. They will throw the energy back, come out to the original place. Again, they'll start taking energy, go to the higher orbit, again come back. So this is a continuous phenomena. Clear, beta?
Yeah.
Right. So this is the amount of energy that you will get. And since energy is always the transaction of energy is always in the form of photons. Hence, energy of the photon, you know that. So energy which it is absorbing is also in the form of h nu, and energy which is emitting will also be in the form of h nu. And that energy emitting will be between energy of the n2 orbital minus energy of the n1 orbital. So I can say that h nu is equal to E naught of z square by n2 square with minus sign minus of minus E naught of z square by n1 square. So if I write that E naught by z square common, I will get this as 1 by n1 square minus 1 by n2 square. This is the equation that you will get. Okay. So this energy which is being emitted, right? Emitted energy can be written as this E naught can be written as something like RH into Z square into 1 by N1 square minus 1 by N2 square, where N2 is always greater than N1. Okay, this formula is the emitted energy formula. How much amount of energy is emitted in the form of photon when electron is de-excited from N2 to N1. It is coming back from our higher orbit to lower orbit when it is coming back. Okay, this much amount of energy has been emitted. Of course, it is the same energy which is absorbed also between these two orbits. Okay, now another way of representing the same equation is hc by lambda is equal to E naught into z square into 1 by n1 square by 1 by n2 square. And hc is a constant value. If I pull that constant value to the other side, I will get this as 1 by lambda is equal to E naught by hc into z square upon 1 by n1 square by 1 by n2 square. So these are also constant values. E naught is a constant value, hc naught is also a constant value. Got it? So if you notice that constant value can be written as 1 by lambda, which is nothing but nu bar, which is wave number, is equal to r into z square into 1 by n1 square minus 1 by n2 square. So r is that constant value, and the value is 109677 centimeter inverse. Okay, or 1 by r value will come across 911.5 Armstrong units. More than r value, we will always be using the value of 1 by r during problem solving. Correct? So therefore, this is the formula. Another way of representing the same formula is like this: r z square into 1 by n1 square minus 1 by n2 square. So it is the same formula in a different representation. One is in the form of energy, one is in the form of wave number. Okay. This r or RH is called as the Rydberg's constant. R or RH are called Rydberg's constant. I hope all of you understood how to figure out the energy difference in the orbits. Okay. Now these are important features from Bohr's model. Now what he was precisely trying to explain us is about hydrogen spectrum. Hydrogen spectrum. Okay. What does that mean? Suppose if you have a simple setup where we have an electrons, we have an hydrogen atoms in an excited form. These are all, let's say, hydrogen atom with a high energy, and they are present between two electrodes here. Okay. If these high energy hydrogen atoms are emitting some radiation out of it, and you let these radiations pass through a small vent, let it pass through a small vent, and then let it fall on a prism, nickel prism, then it will start refracting into various colors here. It will start refracting into various colors. Okay. So here, the way you see the colors would be in the form of simple lines here. Okay. So you will see different color lines here like this. Maybe this color, somewhere you'll see this color, somewhere you'll see this color, somewhere you'll see this color, here you will see red color, like this. You'll always see different lines like this. Got it? That's why this lines what you're getting is called as the emission spectrum. Emission spectrum, or also termed as line spectrum. So since we are doing it for hydrogen, we call it as hydrogen spectrum. Okay. So how many number of spectral lines we are getting becomes an important point to make a lot of conclusion about hydrogen atom. Okay. What are all the important points which are observed here, right? See, these lines we are seeing is when the electron is de-exciting from higher to lower orbit. That means the electron is already there in some 10th orbit, 9th orbit, or 12th orbit, like that. And now they are coming back to the original orbit, which is n is equal to 1. While they are coming back, there are many different ways they can come, right? So imagine if an electron is present in various orbits like this. Got it? If they are present in various orbits this way. Okay. Let's say it started off with this orbit here. From here, one electron is directly jumping. Then there is one more electron which is directly jumping from higher to lower. Here also, higher to n is equal to 1. Any higher to n is equal to 1. Any higher to n is equal to 1. And any higher to n is equal to 1. So it's very specifically noticed that all these spectral lines, okay, all these spectral lines which are falling on the spectrographic plate when the hydrogen is coming back, if at all they are coming to n is equal to 1 orbit, so from any higher orbit, if they are falling to n is equal to 1 orbit, we call it as Lyman series lines. Okay, Lyman series lines. And these lines are only observed in ultraviolet region. Okay, next. If you notice any higher energy orbit, electron in a higher energy orbit, if it is falling on n is equal to 2, then we call this as Balmer series. Balmer series, and it is observed in visible region. They are typically observed in visible region. Okay. And now, if an electron jumps from any higher orbit and it is coming straight to n is equal to 3, this is called Paschen series. Okay, Paschen observed in infrared region. Okay. So like this, every time you find from any higher orbit to 1 or 2 or 3 or 4, there is a particular pattern noticed for hydrogen atom. And we named after those pattern as Lyman series, Balmer series, Paschen series, and so on. Got it? And what are the names for it? So you can see what are all the names. First is Lyman series. Lyman series, where n n2 is fixed, n2, and n1 could be, n1 has to be 1. Okay, and the region in which it is falling is always ultraviolet region. Next one is Balmer series. Balmer n2 is fixed, is falling to 2, and this is observed in visible region. And Paschen series, that is n2 all the way to 3, and this is infrared. Next one is Brackett series, n2 to 4, again infrared. Last one is Fund series, any higher n2 to 5, again infrared. This is what has been observed. Okay. Now, for example, if I analyze only one particular type of orbit, so let's say this is n is equal to 2, and from any higher orbit, it is coming out like this. Electrons are coming out like this, back to 2. Okay. Let's say this is coming from 3 to 2, 4 to 2, 5 to 2, 6 to 2, 7 to 2, and so on. Okay. And one line which is coming somewhere from infinity. This is infinity to 2. Okay. Then how do we represent these lines? This is called as the first line of the series. The first line is the one where lambda is maximum because the energy difference is minimum. And minimum energy means maximum lambda. Got it? And this is the second line. And first line is also called as the alpha line. The second line is beta line. Then we have gamma line, delta line, and so on. And the last line, which is coming from any infinity value to n is equal to 2, that is called as series limit. Series limit, and also known as lambda minimum line. So this is the lambda minimum line of the Balmer series. Same way, every series will have its own lambda max and lambda minimum. Every series will also have its alpha, beta, gamma, delta spectral lines, and so on. Okay. Right. So the next important thing what Bose model has explained is to figure out number of spectral lines. So that means how many lines you are able to see. We are only talking about distinct lines. There might be repeated lines also. We are talking about how many distinct lines we can get. The number of distinct lines which you will get from an n2 orbit will be n2 minus n1 into n2 minus n1 plus 1 divided by 2. Okay. So this is when electron is jumping from n2 to n1. Between these two, how many different transactions it can make. Okay. Or if let's say electron is present in the fourth orbit and is coming to first orbit like this, then how many different ways it can come? See, 4 to 1, 3 to 1, this is 3 and 2, 3 to 1, or it can also come from 2 to 1, or it can go from 4 to 2 and then come to 2, or 3 to 1 directly, or then 4 to 2 directly, and then then 3 to 2, and then it goes to 2 to 1. Now count the number of different lines here. 6 lines you got. So that you can fetch it from this formula also. That is number of spectral lines. Number of spectral lines is simply equal to n into n minus 1 divided by 2. So you can see n is 4. 4 into 3. Okay. 4 into 3 divided by 2. So how many? 6. So you can clearly notice that there are 6 spectral lines. Likewise, if it is you're talking about the spectral lines between two orbit numbers, then you can use this formula as well. Okay. So this is how we can figure out the number of spectral lines present in it. Everybody clear on that? Okay. These are some important pointers we learned from Bohr's model. Okay. Main drawbacks of Bohr's theory, of Bohr's model or Bohr's theory. Okay. It is called as first one, splitting of spectral lines. Splitting of spectral lines. That means the same spectral line, in the presence of magnetic field or an electrical field, it splits into further small lines. If it is splitting in magnetic field, you call it as Zeeman effect. If it is splitting in electrical field, that is called as Stark effect. So Zeeman effect and Stark effect, remember that. Second one, right, is valid for single electron system only. Valid for one electron system. So Bohr's model is only valid for hydrogen or a hydrogen-like species like helium, a helium plus or lithium 2 plus or beryllium 3 plus and so on. It has to be only single electron. Alright. And here we are considering electron as only particle. We do not see electron showcasing its wave behavior here. Correct? These are the main drawbacks of Bohr's theory. Got it? And taking these drawbacks, we try to upgrade the theory further using two more important theories. Correct? So one theory is de Broglie's hypothesis. The other one is Heisenberg's uncertainty principle. Okay. So these two are the parts. We will do it in the next class. Got it? There I'll discuss more in detail about how the uh, how these theories are going to help further to create something called the quantum mechanics, which is introduced by Erwin Schrödinger. So how he came up with the idea of quantum mechanics, how how the quantum mechanics is derived, how is it applicable, from structure of point of view, how it is applicable for our JEE syllabus. All right. So this is the main pointers that we'll discuss in the next class.